Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
For last week and a half, and is giving a talk on anomalous, diffusion, and Polya recurrence.
Yes, thank you very much for the invitation, and I'm pleased to talk here. So I will talk about this, and the plan of the talk is the following. First, I will tell some very well-known facts about random walks, which I understand as a stochastic model of Brownian motion. And then I will tell you another model of Brownian motion, a deterministic model of Brownian motion, which is the simplest deterministic model of the Brownian motion which one can hope to treat with mathematical methods. It's the Lorentz process, which arises from the Sinai billiard. And then in the second half of the lecture, I will talk about Polya recurrence. Actually, in my lecture, I will restrict myself mainly to the two-dimensional case, where Polya theorem says that the random walk is recurrent, and we will see that the Lorentz process is also recurrent. First, I will talk about the case of bounded free flight, which I will tell you what the free flight is. And in the second part about the unbounded case, when we will see there is an anomalous diffusion, and nevertheless there is also recurrence. So that's essentially the structure of the lecture. So let's take then the classical well-known things. So for random walks, I will only consider the simplest random walk, the simple symmetric random walk in dimension D. So X's are IID, and they have these distributions, and Sn is the partial sum. Then the central limit theorem, you know, it says that it converges to a Gaussian distribution with some non-degenerate covariance matrix, and the local central limit theorem says the following, and I put up the central limit theorem to show you the difference what is between the local central limit theorem and the central limit theorem. So the central limit theorem says that the probability of the event that Sn lies in a set increasing like the order of square root of n, square root of time, and a has some asymptotics, and the local central limit theorem gives the finer information. It just says that what is the probability that Sn equals to k. And then about this probability, you of course, so it tends to 0, but if you scale it, then you get in the limit the normal density function. Actually, of course, here k should be an even lattice vector. And then this is okay, so that's the local limit theorem. And in particular, from the local limit theorem, you get that if you put k equal to 0, then you get the well-known asymptotics. That it's 1 over n power d over 2. And as a result, we learned that then the probability that Sn returns to 0 infinitely often, it's equal to 1 if the dimension is 1 or 2, because it's the Borel can't tell you. And then in higher dimension, it's 0. Okay. I also note that there is a stronger version of the central limit theorem, this so-called invariance principle, which says that the random walk as a process in time in a suitable scaling tends to a Wiener process. This is, of course, the same covariance matrix. You can either forget about this black thing, then you get a discontinuous version, and if you want a continuous, a piecewise Wiener version, then this is the statement. So why I told you, because this is really stochastic model of the Brownian motion, it reflects our idea about the Brownian motion, that the Brownian particle it collides with several other particles, and as a result, it changes its direction in a sort of random way. And here we were assuming this. Now, the Lorentz process can be defined by the, first I tell you what a billiard is. Namely, I take, in this case, the two-dimensional torus, but in general I can consider the d-dimensional torus. And in the torus, I consider some scatterers. On the picture, there is only one scatterer, that there may be several scatterers. I assume that the boundaries are somewhat smooth. And I will consider in this lecture the discrete dynamics. So the phase space of this will be a dynamical system. Its phase space will be the following. So I only consider points of reflection. So at every point of reflection, I go the point on the boundary and the outgoing velocity. So this x naught, it's on the one hand a point in the boundary, on the other hand it's a velocity vector on the, in general, d-1 dimensional hemisphere of outgoing velocity. So that's the phase space. The dynamics, it's a discrete map of the phase space. It's uniform motion, and of course uniform motion taking into account the geometry of the torus. And then in the collision there is a specular optical reflection on the boundary of the scatterer. And so this is the dynamics. There is an invariant measure, well-known physicists call it a Liouville measure. It's this measure which is a product of Lebesgue measures on the boundary and in the velocity space, and there is this additional factor which measures the angle of the incoming or outgoing velocity. So that's the dynamical system I am interested in. This is called the Sinai billiard. Or if I assume that the boundary pieces are strictly convex, as on the picture, of course, it is strictly convex. I will not really need, but I just tell you that if I assume that they are just convex, then the billiard is called semi-dispersing. Now, dispersing billiards and semi-dispersing billiards are very interesting subjects of study, because, in fact, if you consider hard ball systems on the torus, a system of elastic hard balls, this system is isomorphic to a semi-dispersing billiard. And so the study of these systems is connected to the Boltzmann-Sinai ergodic hypothesis. But today I will not talk about results related to this hypothesis. I would like to talk about this kind of more refined results for more special cases. Now, what I want to tell you about billiards, some basic facts. First, I want to tell you that a dispersing billiard or semi-dispersing billiard is a hyperbolic, in some sense, hyperbolic system. And I don't want to give technical definitions, but I would rather give you some pictures about it. So first, I will illustrate hyperbolicity with the simplest possible example. So you take in the plane this well-known matrix, and then you factorize this map with respect to the two-dimensional lattice. Then you get a map of the torus, of the two torus. So T is the factorization of that map. And for this matrix, you of course have two eigenvalues, one smaller than one and the other one larger than one, and two eigendirections. So hyperbolicity means, in this example and in general, that there is no eigenvalue on the unit circle. So this is hyperbolicity. This says that in one direction or in several directions, you have expansion, uniform expansion, and in sort of transversal directions, you have uniform contraction. This is hyperbolicity. In this example, I can also very easily describe some building bricks of the hyperbolic theory, namely the stable manifold through a point x is just the continuation of in this case, the stable direction is one-dimensional, so you take in the stable direction the whole line through the point x. Actually, I can show this here. So, yes, something like that. So through the point x, so this is the stable manifold. Of course, it's infinite in both directions, and it also takes into account the toric geometry. So it's a sort of infinite thing on the torus. And the same for the unstable direction. And there is an extensive theory for that. I will not use. I will not go into details. I just tell you two important properties of the stable and unstable directions. Namely, if y is an arbitrary point in the stable manifold, then, of course, the distances of the images of the point x and of the point y tend to zero exponentially fast, because so lambda s is smaller than 1 in absolute value. And the dual statement holds for the unstable direction. So I told that the billiard is a sort of hyperbolic system, and I told you. But the billiard has singularities. Well, I want to illustrate two things. First of all, I want to illustrate, I told that the billiard is hyperbolic, and I have a picture which shows, in a sense, illustrates hyperbolicity. So it's on this picture.
You need some more people. Yeah.
No, okay. Okay, thank you. Perfect. So this is a three-dimensional picture. You have a strictly convex scatterer. You have an incoming front. So this is a velocity direction and a hyperplane orthogonal to this velocity. And to every point of this hyperplane, you attach parallel velocities. So this is a hyperplane, these velocities. And then after one reflection, you get this picture. So this will be a strictly convex manifold. And the distances will be larger. So there will be a uniform expansion. And this illustrates how hyperbolicity works for a dispersing, for a Sinai billiard. So this is what I will use. And there is another fact which I want to mention here, just to have a feeling to what class these billiards belong. Namely, that billiard is a singular dynamical system, and singularity is shown on this picture. So again, I take, now this is two-dimensional, I take this front with parallel velocities for sake of simplicity, and I look at it after one reflection. What happens? So the upper half, so here is a tangency. The upper half goes on without reflection. The lower part has a reflection, and it will be this curved front. So this is continuous, but the derivative, it's a simple calculation. The derivative is not continuous here, so it's a singularity. Actually, yeah, okay. So there is a jump in the, this is the singularity. So the billiards, what is important for us, that billiards are hyperbolic systems with singularities. Okay. Now, by using the billiard, I will define really the Lorentz process, which is the subject of my today's lecture. The Lorentz process is a ZB covering of a billiard, of a toric billiard. So rather than just consider a torus, I consider this periodic configuration of scatterers in the whole plane, and you can guess what the Lorentz process is, but here I can show you. The Lorentz process is this trajectory. So you take a random initial point of the billiard. So you just select one square, in this case, one cube, from which you start according to the invariant distribution, invariant measure, this usual measure which I mentioned. And then the dynamics is the billiard dynamics. So you get this sort of chaotic trajectory. And you feel that it behaves like a Brownian motion, and it's sort of, so I will tell you the results about it. So Sn, I denote by Sn. So kappa will be this vector, the free flight vector. This will be the free flight vector, which I already mentioned. So this is the free flight vector, and then this is the partial sum. It gives you the trajectory, the displacement after n reflection. And I say that, so this kappa is the free flight function. And about a billiard, one says that it has a finite horizon if this kappa is bounded, and it has infinite horizon if it's unbounded. On the picture you see, it's of course unbounded, because in these corridors there are arbitrarily long free flights. And of course you can have a billiard with, so if you have more scatterers, then it will be bounded. So this will be the subject I will be talking about. Okay. Now, let me then go to some results about billiards. Sinai billiard is the same as dispersing billiard. So in this 1970, in this celebrated paper, Sinai proved that two-dimensional Sinai billiard is ergodic and even Kolmogorov mixing, K-mixing. Later, Galavotti and Ornstein also proved that this is a Bernoulli process, saying that it's as random as tossing a coin, so the most random process. The extension of the result to the multidimensional case, it was surprisingly hard, and in an ingenious paper in '87, Chernov and Sinai proved the same thing for higher dimensional dispersing billiards. And then some 5 years ago, Ornstein, Weiss, and Chernov and Haskell, they also proved that Bernoulli property was false in the multidimensional case. Actually, I have to mention one more condition for the higher dimensional case. I will tell you later a bit that we had a project, a different project from ergodicity, and then we found that in this paper of Chernov and Sinai, there was a gap. So actually, they were assuming something about the singularities which was not true. So the singularities have a more pathological behavior than they were assuming. They were assuming that the singularities, I showed you tangencies. So you have tangency, and you should also consider images of tangencies. Now the tangency, if your scatterer is smooth, then the tangency as it is there, it's of course smooth, because it's on the configuration space you have something smooth, and the velocity goes along the boundary of the scatterer also smoothly, so it's a smooth object. But what turned out that after two reflections, you get something which is not differentiable. In most points it is, but in certain points it is not. So even it's not differentiable. And actually for some time it was an open question whether one can save the proof of Chernow and Sinai, but with co-authors we could find that at least in the case when the scatterers are algebraic, then one can save the proof. So this is, so far we only know that it is true for the algebraic case. I will later a bit return to this. Now, once you know that your system is ergodic, mixing, Bernoulli, and so on, you think you know everything. But it's not completely true, because the Bernoulli property, even the Bernoulli property, it says that you have independence. So, of course, you have exponential decay of correlations, but the Bernoulli partition of a billiard, it's an abstractly constructed. Ornstein's construction is abstract. So, about physical functions, for example, the free flight function, you don't know anything because you don't, it's not given in the terms of this abstract construction. It's given in terms of your smooth structure. Your smooth structure is given in the real geometry.
What about the other properties that say also difficult?
Well, yes, yes. So actually, there is a general theory, this hyperbolic theory, and there the real difficulty is to show ergodicity. And then the other properties already come from the theory. Okay? So that's it. Now, so for physical functions like the free flight function, you have to work more. You have to give precise bounds for the decay of correlations, and you have to show the central limit theorem. It doesn't come from the Bernoulli property. So this is a separate problem. And, well, I'm talking about correlation decay. I will talk about correlation decay for Hölder functions. So this is the phase space. So I take functions, these test functions in the phase space, and this is the Hölder property. I remind you that if you have several scatterers, then the phase space has different connected components. So, of course, Hölder property says that on each component you have Hölder property, but it doesn't require anything from different components. So that's the correlation decay, the problem of the correlation decay can be formulated that you want, of course, to bound. You want to bound this correlation, and you say that you have an exponential decay if there are constants, C and C prime, such that for every test function, for every Hölder function, you have this kind of exponential upper bound. And here, this exponent C prime in the exponent, it only depends on the Hölder exponent, whereas, of course, the constant C depends on the functions. That's okay. So that's now the first result for correlation decay, it was given by 1980 by Bunyovich and Sinai for the two-dimensional case, two-dimensional billiards, and finite horizon, so bounded free flight for this kind of dense scatterers. And they proved not exactly exponential decay, a sort of stretched exponential weaker one, but from that they could also prove the central limit theorem and convergence to Brownian motion. So in a sense, they could obtain some beautiful results which were known for random walks. They are also known for the Lorentz process.
So what does convergence to Brownian motion?
Convergence to Brownian motion, well, course, bounded horizon. So then it says that you have this kind of Lorentz trajectory, right? So let me denote it by yt. And then it says that y, say, at divided by the square root of a. So y is a vector trajectory, of course. A is a norming constant, scaling, which tends to infinity. And then this converges weakly to the Brownian motion. This is a continuous trajectory. So the initial point is random. Otherwise, it's a deterministic trajectory. And C0 infinity. So in the space of continuous functions, weak convergence. Okay? Okay, thank you. Okay, thank you for every question, because, thank you. So that's it. So, convergence to Brownian motion. Now, actually, Sinai raised after this result the question about the recurrence of it's a probabilistic, nice probabilistic property. And with Kramli-András, we could give a weaker result. So we could prove a quasi-local central limit theorem. The local theorem would mean that you know the behavior of Sn in fixed points. What is the probability in fixed sets? But this is a moderately increasing set, like log n, log power of n. And for that we received the correct result, the correct asymptotics. And then it also gave a sort of weak form of recurrence that you know that Sn returns to a moderately increasing sequence of sets, infinity of probability 1. In fact, the weakness of result lies partially in the fact that Bunyovich and Sinai had this weaker bound for the correlation decay. Now, in 1998-99, Klaus Schmidt and Jean-Pierre Conz could effectively prove the recurrence of the Lorentz process. Their proof relied upon the central limit theorem of Bunyovich and Sinai and some trick from random walks of Zeitouni. So it was, in a sense, a nice result. However, it was a pretty ad hoc. Both proofs were pretty ad hoc. And, for example, neither proof could be extended to the general case of unbounded free flight. And then in 98, there was a very important paper of Lai-Sang Yang, which considered several models. But for us, it's interesting that it considered dispersing billiards. She considered finite horizon. But in fact, I have to add here that Chernov, I think in 2000, extended exponential decay of correlations to the unbounded free flight. So she proved exponential decay of correlations and the central limit theorem. Actually, the result was pretty general, and our result, which I will talk about, it's also general. So I am talking mainly about this application, recurrence of the Lorentz process. But our theorem, which I will mention, is valid for all kinds of systems. So for Anomalous systems, which are smooth hyperbolic systems in arbitrary dimension, for Anomalous systems with singularities, but then only in the two-dimensional case, and billiards only in the two-dimensional case, and the logistic maps or Hanon maps, one or two-dimensional maps, which are hyperbolic. These are very interesting maps. So Lai-Sang Yang obtained exponential decay of correlation set for all. Now, So I have to tell something about the method how one proves exponential decay of correlation. I will not go very much into the technical details, but I have to tell you something, and I think it's interesting from the general point of view. So if you have a smooth hyperbolic dynamical system, the simplest one, like this matrix I gave you, then how you prove exponential decay of correlations? The proof uses a coding of the dynamics. So one introduces a finite partition, which is called Markov partition. So I showed you that on this linear map in this 1, 2, 1, 1, 1, we had one expanding direction and one contracting direction, unstable and stable direction, and this is, in general, this is the case. So then you, for your phase space, you take a finite partition, and you say that it is a Markov partition if some simple geometric property holds, and this is basic to the whole two applications. So this is some element of the Markov partition, and you take another element, and you take the image. And if, so this is P of dk, T is the map. And if you have this kind of intersection, then it's a Markov partition. So for every J.
So what kind of intersection?
So you have an arbitrary element of your partition and another element.
Right.
And you take the intersection of your element with the image of the element.
Yeah.
So this is Bj and this is Td of k. And this is the intersection you like, you permit.
And what is that?
And I tell you what you don't permit. You don't permit the following thing. You don't permit, for example, this one. So you don't permit. And you don't permit this one. So you only permit when you have an element. There is no intersection, it's fine. But if there is intersection, so I repeat that this is the unstable direction and this is the stable direction. Okay? So in the unstable direction, these parallelograms are increasing, expanding. In the stable direction, they are contracting. So there are various possibilities, and this possibility you like because then your parallelogram goes over in the unstable direction, and you don't permit this thing, you don't permit, and you don't permit this. So this is it clear?
And those are the only three kinds of, I'm not sure.
And you're assuming now it's a parallelogram, and you're partitioning it into parallelograms?
Yeah, I am partitioning it to parallelograms. And so I could formally write the definition, but I don't want to get into formal definitions. Well,
In the unstable direction, we get an interval that contains the original.
yes, exactly.
Stable is the subset.
Exactly. Thank you, exactly. So that's it. Okay. So, and if you construct a Markov partition, then you can do the following. Instead of your original dynamical system, you can introduce a symbolic dynamical system. So sigma is a symbolic dynamical system. It will be actually infinite sequences of the letters 1R. So you had R elements of the Markov partition. So to every point of your phase space, you determine this doubly infinite sequence of symbols, and you say that the nth element, nth symbol is equal to j if the nth image of the point is in Bj. And that's a classical thing. In this way, to your original measure, you get a stationary measure. This is what actually we also learn at school. But if you, this is general for every partition. But if you have a Markov partition, then this map is an almost isomorphy. So it's equivalent problem to consider the original dynamical system or the symbolic dynamical system with the shift. Okay? So that was an ingenious idea actually of Sinai in 1972. And then it also follows that if you have a Markov partition, then you have an induced measure on the symbolic sequences, and it's actually a Gibbs state with exponentially decaying potential. So you know that if you have a finite spin system and you have a Gibbs state with exponentially decaying potential, then you don't have phase transition, first of all, and the only Gibbs measure has exponential decaying correlations. So then, from this symbolic language, you can go back to the original problem, and you have exponential decay of correlations. So that was the classical method. And actually, for this Gibbs...
One short historical remark. So
Sorry.
Actually, the first Markov partition means an Adler and Sinai.
That's Adler and Weiss.
Adler and Weiss.
Yes.
Adler and Weiss, and then Sinai.
Yes, yes. That's Adler and Weiss for the algebraic automorphism of the torus. Correct? But Sinai had a paper in 1972, I think, Gibbs states in dynamical systems, something like that, and there he defined. Absolutely correct. Absolutely correct. Thank you. And one more thing which I want here to mention, because later I will use it, that to this symbolic measure, symbolic construction, there is a transfer operator, which is actually, in the classical case, it's the Markov transition operator. If you have a Markov chain, in this case you don't have a Markov chain, but you have a transfer operator. I don't want, again, to give formal definitions. And for the spectrum of this transfer operator, you have the nice picture that one is the only eigenvalue on the unit circle, and all the other part of the spectrum lies strictly inside the unit circle. So you really, in a one codimensional subspace, you have uniform contraction, and this gives you exponential decay of correlations. So that's the old story. And what Young did, I think that I very briefly tell you some elements of her idea. So she constructed not a finite Markov partition, but a countable Markov partition.
Is it one that you don't have a finite Markov partition?
Yes, I don't have a finite Markov partition, and even if I have a countable Markov partition, actually I mentioned this result of Bunyovich and Sinai in 1980. So they constructed a countable Markov partition, but the construction was very complicated, and also in the higher dimensional case, if you have a Markov partition, then it's an absolutely unsmooth object, not smooth. So the boundary is very, very pathologic. So even if you have a countable Markov partition, then it's not nice. But Lie-Sang used a sort of tricky way to construct a Markov partition, so-called Markov towers. I will not. So it would be too far to tell about it. Perhaps if I have time, I will give some geometric idea of her construction. What I here want to say that the spectrum of this transfer of the transfer operator for her construction did not was not so nice. It only satisfied the so-called Dublin-Forte inequality, which, roughly speaking, is the following type of inequality. Actually, it's a very useful idea. It's a very useful idea that you have, say, this Hölder type norm, and you also have the supremum norm. Now, here alpha is less than 1. So this was the original finite case, apart from this one-dimensional invariant direction. In all the directions you have contraction. But here it's not so. You have an additional term, and that's necessarily so. But even, so this is the Dublin-Forte inequality, and there is a very useful result of Marinari and Ionescu-Turcia from the 50s, which nevertheless says that you have the same spectral picture. So you have one eigenvalue, if your system is ergodic, and in our case it is. So then it has one eigenvalue on the unit circle, and all the other part of the spectrum lies strictly inside. So it's fine. And then it implies exponential decay of correlations. And what she did, that she also proved the central limit theorem by using the exponential decay of correlation and the martingale approximation of your process. It's also a trick of well-known trick of Gordian. Now, I can now talk about our results. So, well, our idea was the following, that as I showed you for the random walk, you can get recurrence by using a local version of the central limit theorem. So you know that what is the probability that you get to 0, and then you use a Borel-Cantelli type argument, right? So we wanted to prove local central limit theorem, and then by using some Borel-Cantelli type. And this is what we did. Well, I don't give, I have a slide with the formulation of this local limit theorem, but it's too technical. There are a lot of technical conditions, so I will not tell it. I just want to tell you that it's a joint work with Tamás Varjú. So what we used in addition to this Lie-Sung method, we used not only the transfer operator. This was a sort of additional idea that one had to use the Fourier transform of the Perron-Frobenius operator. So you have the Perron-Frobenius operator, and kappa is the function you want to prove local central limit theorem for it. So in our case, it is the free flight function. Then you introduce this Fourier transform, and then one has to prove that it also satisfies this kind of Dublin-Forte inequality. And then comes the interesting part of the proof. First of all, in the neighborhood of 0, you show that the spectrum is stable. Namely, if for 0 you have this picture, for 0 you have 1 is the unique eigenvalue in the circle, and the other part is in the smaller circle, then in a small neighborhood you have something like that. So you have a stability. So the leading eigenvalue, for the leading eigenvalue, we have the similar Taylor expansion, which you in general have for the Fourier transform in probability for the characteristic function. And you also know that the remaining part of the spectrum doesn't move much. So for a small neighborhood, the remaining part remains in a bit larger circle, but nevertheless it's bounded away from the boundary of the circle. And by using this expansion, you can essentially apply classical probability theory. So probabilistic ideas. And for proving, I make a remark. So local limit theorem. So in local limit theorem, it gives a precise behavior for points, right? Probability that you are in a point, or you give an asymptotic for the density. Now, as we know from probability theory, the local behavior is governed by the tail behavior of the Fourier transform, right? Tauber type behavior. So that's why we also have to fight with the tail behavior of the Fourier transform. And for that, some compactness trick can be applied. There is actually one additional problem which I only mentioned, namely that if you have, in classical probability theory, you want to prove a local central limit theorem. For random walks, you talk about the probability that you are in a point, right? You are in 0. But if your distribution has a density function, then the local limit theorem says something about the density, right? And they have different forms. And if you have, in a multidimensional case, a general distribution, then you know which part is smooth, which part is discrete. So there is a so-called problem of arithmeticity. And even if you are on the lattice, you should know the lattice distance, because the statement of the local theorem, it naturally depends on the lattice distance, right? So this is a not trivial problem. So this arithmeticity problem is not trivial, but one can answer it. So, okay, now for so what I was saying here, it's the bounded free flight case, finite horizon case. So in this way, we have a local version of the central limit theorem, and by using a Borel-Cantelli type argument, we could also prove a recurrence. So we had a new proof for the recurrence. So that was for the bounded horizon case. Now for the infinite horizon case, I told you that the picture, Chernoff showed exponential decay of correlation. So infinite horizon case, you have the similar results. So our theorem also holds for the infinite horizon case in general, but kappa, this free flight function, is not a bounded function. So it doesn't belong to this Hölder, the space of Hölder function. So we had to change the situation, but not only the method, but the statement is different. In 92, Pavel Bleher gave heuristic ideas for the following convergence. If you take Sn, so now the free flight is unbounded. If you take Sn and divide not by the square root of n, but square root n log n. And then he gave some heuristic ideas. Actually, it was a proof by using 4 hypotheses, which actually are very hard to check.
What is this, I think,
Sn is the Lorentz process, n's collision, so discretized Lorentz process. Okay? And so what he was forecasting, that Sn over square root n log n. So this has a Gaussian limit. So so his proof in general uses these 4 hypotheses, but his paper has very nice observations. First of all, so kappa is the free flight function, unbounded free flight. Then you can see so one has these corridors, right, where kappa is too large. And so this is a sort of geometric problem, geometric probabilistic problem, to give a sort of expansion of the Fourier transform of the free flight vector in the neighborhood of 0. And this is what he obtained. And what he also proved, that first of all, the variance of kappa is unbounded, but the covariance is already bounded for every step. already for N1. So as a matter of fact, the picture is the following. So here you have, if this kappa, in probability theory, one says that this distribution of kappa belongs to the non-normal domain of attraction of the Gaussian law. And so what we proved with Tamás Varjú was the following. First, we could prove that this conjecture of Bleher is true. So Sn divided by square root n log n really has a Gaussian limit distribution. We could also prove that the local version of this theorem also holds. In particular, the probability that Sn in absolute less than 1 behaves asymptotically as C over n log n. Now, in Borel-Cantelli, you know that this is also divergent. So you expect that you have recurrence. And we could also, we could really prove recurrence for this case too. So in a sense, this ends the story. I want to make two more remarks. First of all, so in this case, I was talking about the special function and the special distribution which belongs to this very particular domain of attraction. Actually, our method is also applicable in general for stable laws. So if you have a function which belongs to a domain of attraction of the stable law and you use it for the Sinai billiard, so it's defined by the dynamics of the Sinai billiard, the evolution of this function, then for that you get a stable limit distribution. This is one thing which I wanted to mention. The other thing which I want to mention, that it's a natural question, what happens in the multidimensional case, so more than 2. Now, I didn't say anything about 3-dimensional or higher dimensional cases, and actually this was the project we started to work on some 3 or 4 years ago with Balint, Tóth, not Tóth Balint, these are 2 people, and Chernov. And we almost completed the project to expand this Young method to high dimensional case, but then we discovered this pathology which I mentioned, and the singularities are not differentiable in 3 or higher dimensions. So even 3 dimension is high already in this example, and it's still there. So it's really the singularities in 3 or higher dimensional cases behave in a very complicated way, and so far we do not have a catch on it. But if one can prove correlation decay for the 3-dimensional case, then our method would also give tangents of the Lorentz process in the higher dimensional case, but so far it only depends on the success of treating correlation decay in the higher dimensional case. So I think, thank you very much.
There's a variant of this question when the balls are distributed, say small balls around the photon point. So the location of the bits is also
Random.
So that's the multiversion thing that's an unproblem.
Well, I don't know anything about it. So I was trying to think about the following question, that you have this kind of periodic configuration scatterers, and you just perturb one of them randomly. And you, of course, are sure that everything is the same. But, sorry. Well, I think that if the initial distribution is absolutely continuous with respect to the Liouville measure, then the same is true. Okay? So, no. Actually, it's an interesting question because yeah, so
We could ask for the near opposite dimension of the escaping
yes,
and one would expect it to be 4 dimensions, even though it's at 0 measure.
yes,
These
yes,
are-
yes, yes, yes,
The
yes.
recurrence is quite delicate.
Huh?
It should be a set of 4 dimensions. It's natural to expect that.
Yeah. Actually, if you mentioned recurrence, I tell you one interesting remark. Shimani, in '89, proved the following, that recurrence of the two-dimensional Lorentz process is equivalent to the following statement. You consider a dynamical system in the whole plane with a periodic configuration of scatterers, and you take this dynamics, but just one point. So this is measure-preserving transformation, but the invariant measure is infinite, right? In general, people don't talk much about, except for Aronson, so about ergodicity of these kind of infinite measures. But Shimani could prove that recurrence of the Lorentz process is equivalent to the ergodicity of this infinite measure. So actually, by using this recurrence theorem, we also know that this infinite measure is ergodic. Okay. So you have to leave.
No, I have a little
You
bit.
have to leave. Yeah, okay, good. Because there will be also dinner.
I'm sorry I cannot join
Okay,
because
okay.
I already have some plans for
All
tonight.
right. Okay. So,
But we can do it.
okay.
Do you have an office here? I guess you have an office.
I have an office, but I share it with Imre Bárány, so we can go to the corridor.
Okay, I know. Right, so just next to your office. Right next to my office.
This corridor.
Yeah.
Okay.
Okay, so I'll find you. You'll be there, or
Okay, will you be in his office or?
yeah, I'll be in his office.
Okay, I will come.
Yeah.
Okay. Errefele kell menni? Actually, the household dimension of these Crick's clocks.
Of the past escape.
Yes, but it would be 2, right?
So in the space, so it will be full. So the space of paths you parameterize by the starting point and the direction.
Yes.
Yeah, so it will be 2. Yeah.
Mm-hmm.
Right.
But what do we say that which are escaping? Because so
Which are not recurrent.
for them it's also true. This is what you say.
Right. That's what I'm expecting. So
Uh-huh.
even though they are zero measure,
Yes.
they should be two-dimensional. I mean, here is here is a trivial version of the statement that I need to explain what I mean. Suppose you take a number in